Okay, ladies and gentlemen, let's talk about the power series and in particular the power series expanded. Previously, we have talked about the power series and we say the sum from 0 to infinity of x to the n equals x to the 0 plus x to the first, x to the second, x to the third, x to the fourth. And that's great as long as all of our basic power series is nothing but a standard x. Okay, if on the other hand, our function itself is actually a variety of other functions, whether it be sine x, cosine x, e to the x, any number of transcendental functions, you won't just have these pieces. What you'll end up with is you'll end up with a coefficient times, and if I c to the 0, x to the 0, plus c to the 1, x to the 1, plus c to the 2, x to the 2, plus c sub 3, x to the 3, plus da 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 da. And it's these coefficients that are going to make all the difference in the world. These coefficients are going to be determined by the function that you're expanding with the power function. So what type of function are you using to estimate with a power function? Now, the thing about it is we need to find a way to find each of these coefficients. Well, the first thing we can do is if we go and we take a look at something like sine x. Let's assume our function we're going to deal with is sine x. Now, sine x is something we can easily integrate, something we easily differentiate. And that's fine, but we of course need to start with something easier so that we can work our way up to something more difficult. But this should give us a nice pattern. One thing about a power function, if you're going to expand a power function around some sort of other function, it has to be differentiable derivatives, not just differentiable, but differential derivatives, which means the derivatives themselves can be derived again and again and again and again. So with that, what we're going to do is if I were to take this basic power function, we're going to call it P of x for power function. The thing is, if I expand this around 0, we're going to call it expanded around x equals 0. Now, this is something we've come across in class already. If you expand around 0, that means whatever the functions are that you're dealing with, whatever the estimates that you're using are good estimates somewhere around 0. And as you move away from 0, they tend to get worse. So if we're expanding around 0, that's what we're talking about here. The reason to expand around 0 is because of the special properties of 0. So if this is p to the x, I could plug in 0 for every x, and I don't get 0 here because x to the 0 is 1, so it'll be whatever the coefficient is. But this one will be c1 times 0 to the first, plus c2 times 0 to the second, plus da 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 da. These will all go away because they all have x's in them. Well, so fine, how do you find c1? Well, c1 is going to be left over if there's no x here. How do I get rid of an x to the first? Well, what if I found p prime of x, and I derivated every bit of this power function? Well, first of all, this is a constant and a constant, so that is going to go away. Those are gone, leaving c1, because that's going to, x is going to go away and just become a constant. This, it's going to bring down a 2 c2 x to the first plus 3 c3 x squared. Now, the thing is, when I expand around 0, p prime of 0, I'm going to get c1, that sticks around, plus 2 times c2 times 0, plus 3 times c3 times 0 squared. Those are all gone. And so you say, wait a minute. So you're telling me that the original c sub 0 can be found by plugging in 0 for all x's. But c sub 1, you take the first derivative, and that leaves you just c sub 1. Well, let's see if it works again. P double prime of x, well, that's a constant now. So when I take the derivative of a constant, it goes away. This, I take the derivative, the 2 sticks around, the c2 sticks around, but this is now x to the 0 power, so it is gone. In this case, we have 3 was already here, times 2 comes down now. C3 x to the first plus da, 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 da. And again, if I plug in 0, p double prime of 0, I come up with 2c2 plus, and that's going to go away because of the 0 over here, and p triple prime of x equals, well, that goes away. Here this comes down, I got 3 times 2 times 1, c3 plus, and all the rest of this stuff is going to have x's in it. And they're going to go away. So as you can see, in the first case, I had C1 in the original case I had C sub 0. The first case I had C sub 1. Then I had in the second derivative 2C2, third derivative 3 times 2 times 1C3. Well, before long you should notice a pattern. And that pattern that begins to develop is P prime of 0, P of 0, P double prime of 0, P triple prime of 0, P fourth power or fourth derivative 0, you're going to get just 1 C sub 0, 1 C sub 1, 2 factorial C2, 3 factorial C3, 4 factorial C4, and it is always based on the fact that you get, every time you bring a power down, it's going to be what was a fourth power is now a third power. What was a third power is now a second power. What now is a second power is the first power. So 4, 3, 2, 1. By the time you get to the fourth derivative, you brought down the 4, the 3, the 2, and the 1, and that's where the factorials are coming from. So if by plugging in 0, I can isolate these items, that means if I have some function, f of x, that equals sine x. Well, I could also find the derivative of sine x, and that's why the derivatives must be differentiable. F prime of x equals cosine x. F double prime of x equals negative sine of x. F triple prime of x equals negative cosine x, and F fourth prime of x equals sine of x again. So we're back where we started because fourth round, which we've done before. So we have this, but again, if we're expanding around 0, I can say f of 0, f prime of 0, f double prime of 0, f triple prime of 0, f quadruple prime of 0. And so I can say sine of 0, cosine of 0, negative sine of 0, not theta 0, negative cosine of 0, and sine of 0. Well, sine of 0 is 0. Cosine of 0 is 1. Negative sine of 0 is going to be 0. And negative cosine of 0 is negative 1, and we get a 0 again. So in this case, I have the original and its power function original. Derivative of the power function, derivative of the function, second derivative of the power function, second derivative of the function, third derivative of the power function, third derivative of the function, etc. So that means that whatever this constant or coefficient is here has to equal what's plugged in here. So I can say C sub 0 equals 0. C sub 1 equals 1. C sub 2, well, it's 2 factorial C sub 2 equals 0. 3 factorial C sub 3 equals negative 1. And 4 factorial C sub 4 equals 0. Well, it don't care what these are, because when I divide by 4 factorial, that goes away. When I divide by 2 factorial, that goes away. All I'm left with, and C sub 0 is already 0, I'm left with C sub 1 equals 1, and C sub 3 equals, divide both sides by 3 factorial, negative 1 over 3 factorial. That's the coefficient I go with. So I'm going to have 0, this term goes away, that term goes away, this term goes away. So if I'm putting this all back in a power function, C sub 0 is 0, that term is gone. C sub 2, that is 0, that's gone. C sub 4, that's gone. I'm left with 1x to the first, and I'm left with plus negative 1 over 3 factorial x cubed. If I go to my actual power functions, my well-known and accepted power functions, you will see that indeed sine x starts with x minus 1 over 3 factorial x cubed. And in this case, you see that the fourth term, why it isn't there, is because C4 is going to be 0. C5, not shockingly, is going to be plus 1 over 5 factorial x to the fifth. There's going to be no sixth term. And then the seventh term will be minus 1 over 7 factorial x to the seventh. And that is the power approximation for sine x. Now, this is already something we showed in a previous video. We already showed it summation. But this is how they arrived at it. Using derivatives to actually build the power functions is how you arrive at these things. So by the equating of derivatives of the power function, which is nothing more than the original power function, derive, plug in 0, plug in 0, plug in 0, and equate the derivatives of the function, derive, plug in 0, plug in 0, plug in 0, plug in 0, equate, we come up with a pattern. And that pattern becomes standardized for power functions. That standardization of power functions is P of x equals C sub 0, x sub 0 plus C1 x to the first plus C2 x to the second plus C3 x to the third plus ... where C sub 0 equals P sub 0, C sub 1 equals P prime of 0, C2 equals P double prime of 0 over 2 factorial plus, in this case, you come up with C3, which is P triple prime of 0 over 3 factorial. And that allows you to find C0, C1, C2, C3, etc. Or you could write it alternatively, where it is 2 factorial C2 equals P double prime of 0 plus 3 factorial C3 equals P triple prime of 0. So that is using and expanding power functions based on derivatives. So we say it can be used as a power function and we get the powers, but to get the coefficients, we have to use the successive derivatives. This is what we're going to be using to get some of these derivatives. Now, if we take a look at some of these other things, we will find that this is very much the case.